I love that animation. Part 4 of the heat temperature notes is actually on temperature. This is a little bit longer than the parts 1, 2, and 3, but that's okay. So let's take a look at temperature. The definition, so the scientific definition, I mean, temperature, you might say it's either hot or cold or something like that. Scientifically, it's the average kinetic energy of individual particles in a sample of matter. Remember, kinetic energy is based on speed and mass. Assuming that the mass isn't changing, you're not adding particles or taking particles away, the average KE is basically the average speed of the particles. Okay, so how fast are those particles moving? The faster they move, the higher the temperature, the slower they move, the lower the temperature. So it depends on how fast the particles move. The faster the molecules, the higher the temperature. The slower these are particles, the lower the temperature. Temperature is going to be measured in here in degrees Celsius or Kelvin. Okay, notice Kelvin doesn't have a degree symbol, it's just capital K. In class, we will play an animation that will help us memorize some of this stuff. Okay, so temperature, average speed of the particles, faster they're moving, the higher the temperature, and it's either in degrees Celsius or Kelvin. So let's talk about the scale that you know best, which is probably the Fahrenheit scale. It was developed in the early 1700s by a guy named Fahrenheit. Go figure. What he decided was that salt water, he knew salt water would freeze, and he also knew that salt water froze at a lower temperature than plain water, so he thought, okay, then this must be the coldest that things can get. So he decided that 0 on his scale was the temperature at which salt water froze. Then he made some sort of random tick marks on his instrument that he was developing, the thermometer, and it came out that 32 degrees Fahrenheit is the freezing point of pure water. Right? What he was trying to do was to set it up so that 100 degrees Fahrenheit was going to be body temperature, and as most of you know, 98.6 degrees Fahrenheit is actually the body temperature, so he wasn't that far off, which for the 1700s I think is pretty good. Based on the tick marks that he had on this instrument, it ended up that 212 degrees Fahrenheit is the boiling point of water. All right, so this scale is basically based on how cold he thought the coldest thing could be, and then trying to use body temperature as another one of the reference points on this. All right, so that's the early 1700s. The Celsius scale was actually developed in the late 1700s, so the Fahrenheit scale is around at this point. It's also called the centigrade scale or degree centigrade sometimes. This guy, Celsius, said, okay, well, the Fahrenheit scale is fine, but it's based on something that's not necessarily true, in that the salt ice was colder than the non-salt ice. So what Celsius decided to do is that he was going to make his 0 the freezing point of pure water, which was just, everybody's pure water is the same. We don't have to worry about how much salt is in it, and so 0 is going to be his reference point. Then, before he even made the tick marks, he said 100 degrees Celsius is going to be the boiling point of pure water. So he didn't just put these random tick marks on. He actually thought ahead and say, all right, I'm going to have 0 and 100, and there'll be the tick marks in between. What it worked out to be was that a change of 1 degree Celsius is equal to almost, although not quite, 2 degrees Fahrenheit, which is why water boils at 212 Fahrenheit and 100 in the Celsius scale. Now, then Kelvin came along, and he said, okay, but what does, in both the Fahrenheit and the Celsius scales, we know we can go colder than what they have 0 set at. And so if we're talking about the speed of particles, and that's a measurement of the temperature, what does a 0 or what does a negative temperature mean? that the particles are moving negatively? It doesn't, it's nonsense to him, to Kelvin, that we should have negatives in a temperature scale because it's all about particle motion. So he said, all right, let's do it this way. Let's talk about absolute zero, 0 Kelvin, and at that point, all molecules stop moving because there's no motion, and therefore there's no temperature, because temperature is based on motion, and that will be our lowest possible temperature. We don't know what it is, but that's what we're going to call it. It ends up that 0 degrees Kelvin is equal to negative 459 degrees Fahrenheit and negative 273 degrees Celsius. We're actually going to be doing a lab that will extrapolate this data. It's very cool. We'll do that in a little while. But anyway, so 1 degree Kelvin, however, is the same size as 1 degree Celsius. In order to get to your Kelvin temperature, you take your degrees Celsius and add 273. 0.16, by the way, which we'll do in class. And the Kelvin scale is used for all scientific equations, which we will do later in this unit. So we're talking about gas laws and other things where we're talking about the particles and their motion. All right. Here's this cute analogy that I like about the Kelvin and the Celsius scales. So we're talking about the sea level analogy. So we've got the green or yellow, whichever it is the land, the orange is the bottom of the ocean, and the aqua is the water, and we have our shark. So 0 degrees Celsius, we'll call that sea level. Well, in the Kelvin scale, the bottom of the sea would be negative 273 because it can't get any colder than that. So what is that in Kelvin? Well, we'll come back to that. The top of the land is our 100 degree Celsius reading. At the bottom of the sea, the lowest the temperature can get in the Kelvin scale is 0 Kelvin. Sea level would be 273 K, which is the same as 0 degrees Celsius. And I think that's kind of cool. So you should know that 0 degrees Celsius is the same as 273 K, and that 0 Kelvin is the same as negative 273 degrees Celsius. I don't expect you to write this whole thing down at all. What I would like to draw your attention to are a couple of interesting little things. You could certainly write it down if you want to, but it is not my intention that you do that. If you look up at the Fahrenheit and the Celsius scales, you'll see that they become the same at negative 40. It's kind of cool. I don't know, just the math works out that way. So that's kind of an interesting bit of information, you know, for you when you're on Jeopardy and that kind of stuff. If you look at 0 degrees Fahrenheit, it kind of doesn't mean much. It's negative 18 Celsius, but what's negative 18, you know, 255 Kelvin. So there's not a lot of meaning to 0 Fahrenheit. When you get down to 0 degrees Celsius, we all know that water freezes at 32 degrees Fahrenheit. So that's why I point that out. But again, the number 32 is not particularly relevant to much. But if you go over to the Kelvin scale, you'll see that 0 degrees Celsius is the same as 273 Kelvin, which is 273 degrees higher than 0 Kelvin. All right, just a quick connection to real life. Most of the world, as you could probably predict, use the Celsius scale for temperature. It's the metric unit. When you watch the weather on television, they're always referring to the Fahrenheit temperatures for the day, or the 5-day forecast. However, if you worked for the United States Meteorological Survey, you would see that, in fact, atmospheric temperatures are always referred to in degrees Celsius. So we do connect with the rest of the world a little bit. So that's the end of part 4. Make sure that's up to date. Make sure you've got all the stuff you need, and move ahead to part 5. Thank you.